So today I'll be discussing radiation heat exchange between diffuse gray surface. So diffuse gray surface is a not a black body. In the previous section, or normally we'll be considering the radiation heat exchange between black body, where black body is a perfect emitter and absorber. So there won't be any reduction in the uh, radiation transfer. So whatever is emitted is absorbed. So there's a complete transfer of radiation energy in the case of black body from one plate to another. Both the bodies are black body. For the actual conditions, there won't be any black body. In practical condition, uh, everything will be non-black surface. So there will be multiple reflection, and also there will be emissivity on the surface. So we won't get actual energy transfer of the body. So this diffuse gray surface is the actual case. Which is a non-black body. That is the actual real case. So the heat exchange between the black body we have discussed in the previous session, previous video. So analysis was simpler because black body does not reflect any amount of incident radiation. Right? There won't be any incident radiation reflection. Right? Whatever emitted is absorbed. That's the case of black body. But in practical condition, most of the enclosures have non-black surface, which allow multiple surface reflection. Okay, so in actual cases, there will be multiple surface reflection. Therefore, the analysis of radiation heat transfer or such enclosures become very complicated. The analysis of radiation heat exchange is such enclosure may be simplified, making assumptions. So, in order to solve the problem, we need to find the heat radiation transfer between diffuse gray surface, since this is complex compared to the black body. Okay, so you have to make certain assumption. The very first one is each surface of the enclosure you have to consider it to be opaque. Okay, that means transmissivity. There won't be any transmissivity. Okay, the flow will be zero. The surface be considered opaque, diffuse, and gray. These three terms you have to remember whenever you do the problem between the gray surface. Okay, other than the non-black surface, it should be opaque, diffuse, and gray. Okay, so it should be opaque, diffuse, and gray surface. So this has to be the most important point. And each surface of the enclosed is isothermal. Okay, it is constant, temperature is constant, and whatever surface you be considered, it should be isothermal. And each surface of the enclosed is characterized by the uniform radiosity and radiation. So radiosity is actually whatever the the leaving energy, radiation energy from the surface. The actual out after emissive power reduction. So that's radiosity, and radiation is the 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 amount of radiation energy that falls on the surface. So this is the amount of radiation energy. Radiosity, the amount of radiation that leaves, and this is the amount of radiation that false. Okay, so this is all of the assumption you have to consider for radiation heat exchange between diffuse and gray surface. So this is the representation of say two radiation heat exchange between two surface. It could be parallel. So in general, the radiation exchange between two surface. Okay, that's just not considered parallel. So when it is become parallel, the equation, general equation would change from this. Okay, this would be the general equation. Okay, this wait, I will show you. So this is the general equation for radiation heat exchange between two surface. So this is the first surface having an MC power EB1. Similarly, second surface having MC power EB2. So Q12, 1 to 2 heat exchange, heat transfer, radiation heat transfer occurs. Similarly, from 2 to 1 also radiation heat transfer occurs. So EB1 we know EB1 will be reduced to J1 due to surface resistance. So this is the surface resistance of first surface 1 minus epsilon 1 by epsilon 1 A1. Okay, and similarly there will be EB2 will be reduced by J2 due to the surface resistance in second surface 1 minus epsilon 2 by epsilon 2 A2. So uh, we have J1 and J2. Okay, J1 and J2 be the two radiosity. So between J1 and J2 of the two surface, there will be space resistance of the formula 1 by A F F1. Okay. So here I can write either 1 by A2 F1 or 1 by A1 F12. So both A1 F12 and A2 F1 is same according to reciprocity theorem. So either way, I can write the space resistance between J1 and J2 of the two surface, that is 1 by A1 F1. So that is the F12 is the view factor, radiation view factor. It varies with the different surface on what the shape and the based on condition of the surface. So these are the three resistance in this given condition between radiation exchange between two surface. First, the resistance in the first surface. This is second one, and the space resistance. So simply apply to the equation Q. The heat current is the overall potential difference by total thermal resistance. So this is the general equation. Sigma T1 raised to 4 minus T2 raised to 4. So T1 and T2 is the surface at the extreme end. Okay, the first and the second surface. And let's write all the thermal resistance. 1 minus epsilon 1 by epsilon 1 A1 plus 1 by A1 F1 plus 1 minus epsilon F by epsilon 2. So this is the general heat current or heat radiation heat transfer between two surface. So from this I can write the various condition whether it is parallel, concentric, sphere. So next we can discuss the different types of radiation transfer for various condition. So that's a simple representation on the radiation heat transfer on a surface. As you can see, I have to know what is epsilon, EB and rho. So epsilon will be the emissivity of the surface. So the surface I am considering. Okay. So the emissivity which varies on the different types of surface. So whatever it is, emissivity is the epsilon is the emissivity of the surface, and the EB is the emissive power of the black surface. Okay, we'll be having gray surface, but EB means the total, and the emissive power that can be emitted by that body. It's the emissive power of the black surface. When we consider black surface, is it can emit all everything, all the radiation, right? Except of the emitter and absorber. So EB is the emissive power of the black surface. So this is J is the heat transfer, radiation transfer, and G is the radiation, and J is the radiosity. But in actual case, this will be happening. This J and J will be the combination of uh, epsilon EB and rho GP. That will be the surface with the reflection. So this is without reflection. There will be J and J. But when radiation balance on a surface with reflection, uh, the surface will be reflecting with the rho. Rho is the reflectivity constant rho, and epsilon is emissivity. So we won't be getting EB, but only epsilon EB. So fraction of the total the MC power will be reduced. Similarly, G is the radiosity. That means the total radiation energy that falls on the surface, but due to reflectivity, it also reduced to multiplied by the fraction rho. So as you can see, this is surface and EB is the MC power. Okay, the total MC power of this surface, but on the output side, we will be only getting J. Okay, the radiosity J will be only getting due to the surface resistance. Since this surface is having an epsilon or emissivity, there will be an resistance in this surface called surface resistance, which is of the formula 1 minus epsilon by A epsilon. This is the general formula for surface resistance 1 minus epsilon by A epsilon. So due to this surface resistance, this EB or MC power of this body will be reduced. Initially we'll be considering black surface because then only will be have the total energy stored. But the real cases we know there will be resistance or emissivity for the surface. So EB get reduced to J. Why? Due to the surface resistance 1 minus epsilon by A. Okay, so I will show you the further equations. So due to the radiation exchange, the energy leaves the surface by emission and reflection, right? While the surface gain energy by radiation, G. So therefore, the rate of net energy leaving, net energy leaving a surface Q is the difference between the radiosity J and G. So you can see J is written as epsilon EB plus rho g. Epsilon EBJ is written as epsilon EB plus rho g. You can see. So uh, J is the sum of epsilon EB. So this won't be a perfect emitter. So the fraction is reduced due to emissivity. So epsilon EB plus rho g. Okay, that fraction is reduced due to the reflectivity rho g. So that sum will be radiosity of the surface. Okay, this is the maximum. The thing that will be getting the output. This is supposed to be the input EB. This is the actual MC power or radiation power stored in the surface, but only the J is what we getting the radiosity due to the surface resistance, which is the combination of radiosity is the sum of energy epsilon EB plus rho G. So I can say this Q. Q is due to the uh, just like analogous to electrical current. I can say Q is due to the difference in potential. Here, difference in the MC power. J is the EB is the actual initial power, but it is reduced to J due to the difference between the MC power at the point EB and J. There will be net uh, radiation transfer. Okay, then radiation transfer will happen, or radiant rate of net energy leaving the surface Q will be, which is the difference of the J and G. J is the one leaving and G is the one coming. Okay, radiosity and radiation. Okay, well, the reason why I multiply with A in the equation Q is equal to A into J minus G is we are considering surface having area A, not a unit surface. Okay, if it is considering a unit surface of area, unit meter square will be Q is equal to J minus G. The net transfer or energy leaving the surface Q will be J minus G. But for a surface having area A, it will be Q is equal to A into J minus G, where J is epsilon EB plus rho G. So this is the uh, for opaque diffusion gray surface alpha plus rho equal to 1. So putting this value, it will be epsilon EB plus 1 minus epsilon into G. So the final Q will be A is A into epsilon EB minus J by 1 minus epsilon. Okay, and this is the radiosity radiation equation G is equal to J minus epsilon EP 1 minus epsilon. So this will be the final equation comparing. If I'm, so we can compare this to analogy to Ohm's law or electrical current. Q is the here the Q or the radiation heat transfer is analogous to the current in the electric circuit, and the resistance, the surface resistance in here in the radiation heat transfer is analogous to the electrical resistance. Similarly, the potential difference here you can see the potential here is also there is a energy difference created due to the emissivity. You can see there will be J and EB. So EB minus J is the potential difference compared to the electrical circuit here. Okay, this due to this potential difference, the Q happens or radiation transfer occur. Then this is a formula of surface resistance. General formula of surface resistance having emissivity epsilon 1 minus epsilon by A epsilon. Okay, so and one important point you have to discuss is surface resistance for black body is 0. Okay, the R will be 0 for a black body, and for black body epsilon will be 1. Why? Because it's a perfect emitter. What really happens is J is equal to EB. Okay, there won't be any reduction or a potential difference. EB and J will be same. Okay, so it's a perfect emitter, black body. So therefore the net heat flow or black body thermal will be 0. So there won't be any net heat flow. It will be simply a perfect emitter and absorber, but there is no flow of heat flow or radiation energy, but there is no electrical resistance and also potential difference. EB minus J is the potential difference due to which the heat transfer or radiation transfer occur, right? So for black body, there won't be any differences. Both the terms are equal. So heat flow for a black surface at thermal equilibrium will be 0. So this is the radiation heat exchange equation according to various situation. Okay, the first one. Okay. let's look at the first enclosure. You have a small object which is inside a large cavity. So this small object is having an area A1, temperature T1, and epsilon 1 emissivity epsilon 1. Similarly, the enclosed surface also have an area A2, temperature T2, and epsilon emissivity epsilon 2. So the radiation, if you take the ratio between these two, epsilon A1 by A2, A1 is a smaller surface compared to A2 the larger one. Okay, the ratio will be A1 by A2, right? So A1 by A2 I can write approximately equal to 0 because this is A1 is a very small value compared to A2. So A1 by A2 will be 0. F12 is 1. Radiation view factor 1 to 2 is 1 because any radiation that is emitted by this small bodies fall on this enclosed cavity. So the F12 or radiation view factor will be 1 since all the radiation emitted by this body is absorbed by this enclosure. Okay, so F12 is 1. Why? Because it is enclosed by this uh, of the for a small body. So Q12 radiation heat exchange which you wanted to will be A1 6. So the radiation heat exchange between this for this condition will be Q1 to A1 sigma epsilon 1 T1 raised to 4 by T2 raised to 4. So reducing all the terms from the actual general equation just we have discussed. Will be the general equation for this condition. Next, for infinitely large parallel, we have a radiation heat exchange between infinitely large parallel. The general equation. So for infinitely large parallel, area will be same, right? So both area will be same height, same length, same thickness. So A1, A2 will be same. Also F1, 2 will be 0, right? The view factor can be taken as 1 because the radiation emitted from one body fully falls on the other. So similarly, just like in this case, F1 is 1. So the equation for infinitely large paraplate will be this one. Okay. Similarly, you can write down infinitely long concentric cylinder, concentric PS. So just have to learn this final formula for all these specific figure. Don't need to derive it once more. Okay. Just learn for large paraplate, long concentric cylinder, concentric PS. Just learn this final formula. Simply substitute the given values. Okay.